Now question number 28 reminds me of the following analogous mathematical problem. We have to find the limit as n tends to infinity of the expression square root of 1 plus square root of 1 plus square root of 1 and so on, and this particular sequence is repeated n times. Note that n tends to infinity. Now the way to do this is to express the limit as, let us say, L, and we rewrite the equation as L equals square root of 1 plus, now we are going to write this expression in the form of a limit, but we notice that now in place of n there are only n minus 1 terms left, because one of them has already been written, that is this one has already been written, and so what we get is limit square root of 1 plus square root of 1 plus and so on n minus 1 times, and of course n minus 1 here tends to infinity. Now we can observe two things. The first thing is, since the number of terms here is so large, in fact it tends to infinity, n minus 1 tends to infinity, we could have an additional term, an additional square root of 1 at the end over here, and it's not really going to affect the value of the expression. So I could have written n times in place of n minus 1 times. That is my first observation. The second observation is, since n minus 1 tends to infinity, n also tends to infinity. Now in doing this manipulation, what I have got essentially here, this limit is nothing but my original limit, which was L, and so I can rewrite the equation as L equals square root of 1 plus, and the limit which I have written here is L itself. So to find L, I can square both sides, so this implies that L square equals 1 plus L. I get a quadratic equation, and I can solve it for L using the formula method and accept the positive value of L, because if you look at the first equation over here, if you look at the left hand side especially, clearly the left hand side must be positive, so you reject the negative root of this quadratic and accept the positive root, and so you get the answer L is equal to 1 plus square root of 5 divided by 2. Now let us return to the problem in which we have been given a certain network of capacitors. The capacitors used are 1 microfarad capacitors and 2 microfarad capacitors, and in this particular diagram I have not written the units, which must be assumed to be microfarads everywhere. We have been asked to find the effective capacitance across terminals A and B, that is, looking into the circuit in this direction, we want to find what is the effective capacitance, which we will call C. Now, as per the data in the question, there is a certain unit of the circuit which is repeated infinite times. So the unit I'm talking about is this particular unit. You notice that it appears once here and then it appears again over here. It appears yet another time over here, and this particular unit of 2 microfarads and 1 microfarad is given to be repeated an infinite number of times until finally you reach the last unit of 2 microfarads and 1 microfarad over here. Notice that in addition to this infinite sequence of 1 and 2 microfarad capacitors, there is this individual capacitor of 1 microfarad over here, which does not belong to any unit of this sequence whatsoever. To solve the problem, let us first recall that the capacitance as viewed across terminals A and B is equal to C. Now what we do is to temporarily remove this part of the circuit. That is, we may imagine that we physically cut this wire over here and this wire over here, and what we get then is the remaining part of the circuit as follows. Now if you look at this circuit, you realize that once again you have an infinite number of recurring units. That is, we have a unit of 2 microfarads and 1 microfarad which repeats over here, and it repeats an infinite number of times, and finally it ends in a similar unit over here. And finally, just like in the original circuit, there is an extra 1 microfarad capacitor over here which does not belong to any of these recurring units. In short, when you look at this particular circuit through these two terminals in this particular direction, you will not see any difference between this circuit and the original circuit given in the question, and hence the capacitance of this circuit as viewed through these terminals in this direction is going to be identical to the effective capacitance of the original circuit, and hence it's going to be equal to C. So to find the capacitance of the original circuit, we must bring back the section that we just cut out. So we bring it back and we put it in the proper place like this. So this is our original circuit, and if you look at it carefully, we realize that there is a capacitance C, which is the effective capacitance looking through terminals A and B, and there is a 1 microfarad capacitor over here and a 2 microfarad capacitor over here, followed by the same capacitance C over here looking through these two terminals. In other words, the circuit can now be reduced to the following. I'm going to cut out this part of the circuit and I'm going to replace it with a capacitance C. So I'll first cut it out like that, and now I draw the equivalent capacitance, which of course is C. Now in my next step, I reduce the complexity of the circuit by replacing this particular series combination, that is 2 microfarads and C, with the effective capacitance. So I just cut it out. Of course, the effective capacitance, I can write it over here, is going to be 2C upon C plus 2. So I'm going to cut this out like that, and I replace it with the capacitance (2C) divided by C plus 2, like that. And finally, we know that this particular parallel combination of capacitors is effectively 1 microfarad plus 2C upon C plus 2, and of course we know that it's going to be equal to C. So on the right hand side of the equation I write C, and then when I simplify this equation, I get a quadratic, which is C square minus C minus 2 is equal to 0. And when I solve this quadratic equation and accept the positive root while rejecting the negative root, I finally end up with an answer of C equal to 2. And of course I have consistently assumed that the units are microfarads, so I put a microfarad unit here at the end. The effective capacitance of this infinite network of capacitors is 2 microfarads.